Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the first lecture of Module 6. In Module 6, we will learn about seismic waves in a spherical earth and body wave travel time studies. So in the lecture today, we will cover the concepts such as seismic waves in spherical earth, ray path and travel time, ray path and travel time in polar coordinates. Then we will be having the summary of today's lecture. So, in the seismic waves in spherical earth, why we not consider the flat layers? If you look at the geometry of source and receiver at the shallow surface or the shallow subsurface, like when you are studying in the crust or maybe up to uppermost mantle, when you compare the distances with the radius of the radius of the earth is maybe around 6371 kilometer, and when you are studying the earth maybe within the crust or maybe within the mantle, then the distance or the depth that you are interested in maybe less than maybe 100 or 200 kilometers. So in that case, if you compare these two depths like 200 kilometers with 6371 kilometers, then you can easily understand that the 200 kilometer is almost negligible with respect to 6371 kilometer. So basically, when we apply the Snell's law for the flat layer earth, that is R1 sine I1 by V1 is equal to R2 sine I2 by V2, then for the studies near to the surface, these R1 and R2, these are the radial distances from the center of the earth, can be neglected. So what you will be remained with sin I1 by V1 is equal to sin I2 by V2. So that is what it is written. The ray path between the source and receiver are short enough, or maybe you can say less than few hundred kilometers, that the earth's curvature can be neglected. And that can be done for studying the structure in the crust and the uppermost mantle. And if suppose we want to study the deeper earth that may involve the greater distances and the greater depth, then we need to take consideration the curvature of the earth, that means the spherical earth, to study the deep earth structure. Now look at this diagram where we are considering the earth as a series of concentric spherical shells of uniform velocity material. So this is the one shell where you can say the velocity above is V1 and here you have velocity V2. There is a ray that is reflecting at the top of the T2 layer, and then it is refracted and then again refracted and then moving in this direction. So by Snell's law, we have R1 I1 by V1 is equal to R1 sin I1 dash by V2. At this particular interface, we are applying it. And if we look at this particular diagram here, or you can say if we look at this particular triangle over here, then you can say that sin I1 dash is equal to ON, this is this, divided by this radial distance R1. Likewise, if we consider this particular triangle, then sin I2 will be equal to ON by R2. And then if we take ON from both of the equations, then what you will get R1 sin I1 dash will be equal to R2 sine I2. So that is what it is written here. And then when you will keep this into this particular equation, then what you will get the Snell's law for spherical earth. That is R1 sin I1 by V1 is equal to R2 sin I2 by V2, which means the ray parameter for the spherical earth is given by R sin I by V, where R is the radial distance from the center of the earth. So for different rays that are emerging from the source will be having the different ray parameters. So let's suppose this is the source over here, which is R0 radial distance away from the center of the earth. Then P, that is the ray parameter, can be written as R0 sin I by V0. So that I is basically for this particular ray, and similarly you can write the value of the ray parameter for this ray. So for both of the rays, the ray parameter are different because the source is scattering the ray in all the directions, or you can say the rays from the source are leaving at different angles with a different ray parameters. As the velocity increases with depth, ray eventually bottoms and turns upward when I is equal to 90. So in this case you can say the rays are going down and then finally it becomes horizontal and then bottoms up and then recorded at the receiver. At the bottoming depth, that is, or you can say at a radial distance Rp, that is the radial distance for the bottoming depth. So R is equal to Rp and P is equal to Rp sin 90 by Vp. Then finally you will get Rp by Vp. So ray parameter at this particular point will be Rp by Vp. So different rays with different P bottom at different depth. So if you look at this particular value, P is equal to Rp by Vp. So if you calculate Rp, that is P into Vp, that means the rays that are having different ray parameters will bottom at a different depth. Now let's consider this case here where you have one ray that is having the ray parameter P after traveling a distance of T, and after traveling for a time T covering a distance delta, that is the angular distance, there is another ray having the ray parameter P plus dP traveling for a distance of T plus dt and covering a distance of delta plus d delta. Then if you will consider this particular triangle here, because the d delta is very small, so this can be considered as a hypotenuse of this particular triangle. So sin I can be written as V0 dt divided by R0 d delta. Then we can rewrite it as dt by d delta is equal to R0 sin I by V0, that is P. That means the slope of the travel time curve in the case of spherical earth as well can be found out by the ray parameter, or you can say the ray parameter of the travel time curve in the spherical earth is equal to the slope of the travel time curve. Thus, similar to the flat layer case, the ray parameter is the reciprocal of the apparent velocity along the surface Cx. So P is equal to 1 by Cx, that is Cx is d delta by dt, and finally the ray parameter will be equal to dt by d delta. Hence the ray parameter can be measured from the differences in the arrival times at nearby stations. Conversely, the slope of a travel time curve t delta is the ray parameter of the ray emerging at a distance delta. Now define the ray in the polar coordinate. So for this purpose, let's consider the point P along the ray, that is this point, and it has the polar coordinate r comma theta, and consider a small portion of this ray such as this one, and which is having the ds value and then it is subtending a angle of d theta over here at the center of the earth. Now from this particular triangle here, you can see if this is d theta, then it can be equal to r d theta. So using the Pythagoras theorem, we can write ds square is equal to dr square plus r square d theta square, and sin I is equal to r d theta by ds. When we substitute it using Snell's law, then p is equal to r sin I by v, and we can write sin theta as r d theta by ds, then it will become r square d theta by v ds. Thus the above equation can be rewritten as this equation: r4 by p square v square is equal to dr by d theta square plus r square. Then we can manipulate to obtain d theta, that is the angular distance by the ray after covering a distance of ds along the ray. Then this d theta can be written as plus minus p dr by r in bracket eta square minus p square to the power 1 by 2. Here this eta is equal to r by v. Integrating this expression from the surface r0 to the deepest point on the ray. So let's suppose this is the surface of the earth and ray is traveling like this. So ray is bottoming up somewhere over here. So we will first calculate the angular distance the ray is covering for coming up to this bottoming point. Then we will double that angular distance to calculate the total distance covered by the ray. So that is what it is happening here. Delta p is equal to integral over d theta, that is equal to 2p integral from the surface point, or you can say the point where the ray is bottoming up, that, and wherever the ray is starting from the surface r0 to rp, that will be doubled, that is dr by r eta square minus p square to the power 1 by 2. This integral gives the angular distance delta traveled by the ray with ray parameter p in the earth with a velocity distribution br. So the integral expression for travel time of this ray can be given as p square v square by r square is equal to r square d theta by ds whole square, and that can be rewritten as 1 minus dr by ds to the power square. So that a portion of the ray path, that means ds, can be written as plus minus r by v dr by eta square minus p square to the power under root. Thus the total travel time can be calculated after dividing this distance by the velocity, and that will be equal to 2 into 0 from r0 to rp eta square dr by r in bracket eta square minus p square to the power under root. If we compare these expression for travel time and this expression that the ray is covering the angular distance with the flat layer geometry that we did in the previous class, then what you will see, both the expressions are quite similar to each other. So let's compare them. So this is the distance traveled by the ray when we are considering the flat layer assumption, that is 2p integral 0 to zp dv divided by u square minus p square to the power under root, and this is the angular distance covered by the ray in the spherical earth, and that is 2p r0 to rp dr by r eta square minus p square to the power 1 by 2, where this eta is equal to r by v. So if we compare the travel time in the flat layer case, those are also quite similar to each other. So these expressions, or you can say these integral expressions for the angular distance and the travel time of a ray in spherical geometry are analogous to those of the distance traveled and the time taken by the ray in the layered material. So for flat geometry, we observe that the usefulness of describing the travel time curve in terms of the slope, the ray parameter p, and the time axis intercept of its tangent tau. To do the same for the spherical geometry, we can write our travel time in the similar way, like that is p delta p plus tau p, that is the intercept time. And it can be rewritten as, if we want to calculate the intercept time, then that will be Tp minus P delta P. And when we incorporate these values here, P total travel time and the angular distance from the integrals that we have over here, then what we will get, the intercept time with respect to P, that is 2 from R0 to Rp, eta square minus P square to the power under root by R dr. So this formulation we can use to invert travel time curve to find the velocity structure. So this expression is used very extensively in case we want to find out the structure of the earth. So, and that can be done by doing the inversion of those travel time curve using this particular expression. So the summary of today's lecture is, to study the crust and upper mantle, the flat layer assumption is more convenient, whereas to study the structure of the deep earth, spherical earth is more concise. The ray parameter for the spherical earth can be given by this expression, P is equal to R sin I by V. Ray leaving the source at different angles have different ray parameters. Different rays with different P, bottoms at different depths. Ray path and the travel time for flat layer and the spherical can be visualized as P is equal to 1 by Cx is equal to 1 by d delta by dt is equal to dt by d delta. And dt by d delta can be equated to R naught sin I by V naught, that is the ray parameter. And the expression in the integral form for the spherical earth for the travel time and the angular distance are this, and for the angular distance with respect to ray parameter is this, which is quite similar to the flat layer earth case. So this is all for today. These are the references, and we will be meeting in the next lecture, that is the lecture 2 of module 6. Thank you so much. Bye bye.